Hello everyone. Today we will learn Chapter 3, System Analysis in Time Domain. In this chapter, we will learn the description of LTI system, the response of the CT LTI system and the DT LTI system. And we will also learn the impulse response for the system property description. In this lecture, we will first introduce the description of LTI systems in time domain. For a continuous time LTI system, the input and output are both continuous time signals. Here, the LR circuit is one CT LTI system. And we use this voltage source as the input, and the current is the output. According to the KVL, we can get the equation. That is to say, the input and output relation for this first-order LR circuit can be described using the first-order differential equation. Here is an LRC circuit. We also use the voltage source as the input and the voltage on the resistor as the output. Without going through the detail, we can get the following equation. That is to say, the input and output relation of the second-order LRC circuit can be described using the second-order differential equation. In many engineering applications, the mathematical models are similar differential equation, and we can use the differential equation to describe the relation between the input and output for CT systems. For a CT LTI system, we can use a linear differential equation with constant coefficient. Here is the mathematical form. In this equation, the linear is corresponding to the linear system, and the constant coefficients corresponds to time invariant. Besides the linearity and the time invariance property, the CT LTI system also has other properties. One is differentiation property. When ST is the input and YT is the output, then when the input is the first derivative of SOT and the output is also the first derivative of YOT. The other is the integration property. When the input is SOT and the output is YOT, then when the input is the integration of SOT, the output is also the integration of YOT. Here is one example. Given S sub 1 OT, and here is the output for this input. Now let's determine what is the output for this S sub 2 OT. Here is the solution. For this question, we should first find the relation between S sub 1 OT and S sub 2 OT. Based on these two waveforms, we can find that S sub 2 OT is the integration of S sub 1 OT. Thus, according to the integration property, we can that Y sub 2 OT is also the integration of Y sub 1 OT, and we can get the final result. Here is another example. Now, given S sub 1 OT and its output, let's determine what is the output for this S sub 2 OT. Similarly, we should also first find the relation between S sub 1 OT and S sub 2 OT. We can find that S sub 2 OT is the integration of S sub 1 OT, Thus, y sub 2 of t is also the integration of y sub 1 of t. For this y sub 1 of t, it is the summation of two impulse signals, and we know that the integration of the impulse signals are the step signals. Thus, we can get the final result. For the DT-LTI system, the input and output are both discrete time signals. The moving average system is one type of DT-LTI system. Here is a three-point moving average system. The input and output relation can be expressed in this equation. And we can find that the input and output relation of a DT system can be described using a difference equation. Here is a flash to interpret this averaging system. Now, the average of these 3 points is the output. The DT system can be described by the difference equation. We can use forward or backward difference equation to represent a DT system. For causal signals, background DEs are often used. For a DT-LTI system, we can use a linear DEs with constant coefficients to represent it. Here is the representation. In this equation, the linear DE corresponds to the linear system, and the constant coefficients corresponds to time invariant. For this DT-LTI system, we can get its impact form. In this equation, A sub I and B sub G are coefficients, and A sub 0 is equal to 1. Besides the linearity and the time invariance property, the DT-LTI system also has other properties. One is difference property. When the input is SOK and the output is YOK, then when the input is a difference of SOK, the output is also the difference of YOK. The other is the summation property. When the input is SOK and the output is YOK, then the summation on SOK is the input. The summation on YOK will be the output. Here is one example. Given S sub 1 OK and its output, let's determine what is the output for S sub 2 OK. Here is the solution. We should first find the relation between S sub 1 OK and S sub 2 OK. From these two figures, we can find that S sub 2 OK is the difference of S sub 1 OK. Thus, according to the LTI properties, we can get the output is also the difference of Y sub 1 OK, and we can get the final result. Now, let's give a summary. In this lecture, we introduced how to describe a CT-LTI system. It is a linear differential equation with constant coefficients. We also introduced some properties for CT-LTI system. One is differentiation property. The other is the integration property. For the DT-LTI system, we can use a linear difference equation with constant coefficients to represent it. The DT-LTI system has difference property and summation property. That's all. Thank you. See you next time.